And then we're going to do some calculations with titrations. And then we're going to start balancing what we call redox equations. These take practice, so today don't expect there'll be a few of you that will, may get it right away, but most of you will be confused when you leave, and that's okay because you have to practice, okay? So, and then we will practice again on Monday, okay? So you have to pay attention to your rules. I actually printed those out for you. I think I have enough for everybody if you didn't bring them, but they're on Blackboard, okay? So, all right, if you were there for the titration lab, you've also watched the video, hopefully. So this should be old news to you, but we're going to go through and talk about the titration a little bit more in detail, kind of go back to talking about what we did in lab as well. Okay, so a titration is one of the most probably used techniques in the chemistry lab. So most every chemist that's been in the lab for any amount of time has done a titration before. Your environmental chemists do them, probably, I don't know, at least 50 a day probably, trying to titrate different solutions or whether they're testing sample water, things like that. Okay, so we've done an acid-base titration. So we had HCl and we had NaOH were our two solutions that we used. So we're going to kind of, as we go through, I'll talk about both of those. Okay, so the titration is a process where you have one reactant and you carefully add it to another reactant. Okay, and then the volume that you use or that is required has to be measured. Okay, so that's where you had to measure the volume used. Okay, does anybody remember if we put the NaOH in the burette or do we put it in the Erlenmeyer flask underneath? NaOH in the burette, right? Okay, typically we do that just because it's a little bit safer. Our bases aren't quite as messy to deal with as our acid, so we usually put the acid in. It's our HCl solution. It was very dilute for you guys, but that's not always the case for every reaction. But basically we're doing a neutralization reaction. We're adding a strong base to a strong acid. Okay, and so what happens when we react an acid and a base? What do we form? Okay, it neutralizes and forms what? I remember? Salt. So we formed NaCl plus water. Exactly. So that's what we're doing. That's why you could put it down the drain because it was neutral. Okay, your indicator. So you use phenolphthalein as your indicator. So we're going to talk a little bit more about it. There's all kinds of indicators. In Chem 2 right now, we actually used a universal indicator, and we saw how it changed all kinds of colors. There's bromothymol blue. There's lots of different ones that you can use. So in Chem 2, we actually learn which ones are the best to use for certain situations. Okay, but for you guys, we use phenolphthalein. It's very common. The reason for that is because the indicator color changes at a specific pH. Okay, what do you think that pH would be? pH of our scale 0 to 14, I know it's a little, okay, 7. Why? That's neutral, exactly. So when you add a strong acid to a strong base or vice versa, okay, when it's neutralized, the pH should be 7. So phenolphthalein turns that light pink and then goes colorless after 15 or 30 seconds at a pH of 7. So that's why it's a good indicator to use, because that's what we're trying to do. Okay, we have a standard solution. So the titrant is a standard solution. So the titrant is what goes in the burette. That's what you're titrating with. Okay, and it's our standard. So of the two solutions, you have to have one that's a known concentration. Okay, so I think in the lab it was 0.2136 was our molarity for NaOH. Okay, so you were given that before you ever started the reaction, before you ever started. Okay, so that was your standard. Okay, you have to know one or the other. Okay, but in this case, the HCl was unknown, so we were trying to find the concentration of the HCl. Okay, and so we did this by titrating with the standard or the NaOH. Okay, your endpoint ideally should be the same as your equivalence point. Okay, so equivalence means that you have the same moles of acid and base to neutralize the acid and the base. Okay, and so your endpoint is when it turned color, when you saw it hopefully be that light pink and go to colorless. That's your end point. Okay, your equivalence point means they should have equivalent moles, should also be the same. However, if you went too far and you got fuchsia, then you went past your end point, right? Okay, so you went past the equivalent point. Okay, so the burette is what we use to deliver the titrant. Okay, we have an indicator, or we could use a pH meter. So in Chem 2, we have pH meters hooked to our computers, and so we don't have enough for everybody to use one. Okay, but we put the pH meter down into the solution, and then we read it from the computer. So you can also use a pH meter as well. Okay, so the first thing we have to do is prepare your burette. Okay, one thing to talk about the burette real quick. So everybody probably noticed that it looks like it reads backwards, right? So up here was 0, and then down here was 50. Okay, do you remember how many decimal places you had to read the burette to? 2, exactly. Okay, the reason we have to do that is because we use a burette because it is more precise than any of our other instruments that we've used or glassware that we've used so far. Okay, so you need to measure to 2 decimal places. Okay, so you're measuring a lot more precisely. Okay, and it is backwards, so yes, you start at 0.00 or wherever you landed. Okay, so we fill up our burette with the NaOH in the lab. That's what we used. Okay, and we fill it up past the 0 mark. Okay, so we did that over the sink, and then we kind of let a little bit out to try to get it right at 0 or a little bit below that. Okay, you want it to be below. It needs to be in the calibrated area. Okay, it says to condition the burette. Okay, what do you think condition means? Okay, clean it. Okay, so it needs to be clean. And then what else did we do in the lab? Okay, air bubbles, that was good. Exactly. So before we actually filled it all the way up, you rinsed it with some small portions of NaOH just to be sure that all the sides of the burette are NaOH and not water or whatever else that could contaminate your sample. Okay, then we checked for air bubbles and leaks. Okay. Some of you may have used your notebook or whatever. You can get a card with a line on it if you want, but that just kind of helps you read the bottom of the meniscus because it's hard to see sometimes. Okay, so we had to take the initial volume reading. Okay, so we recorded this to 2 decimal places, and we looked at the bottom of the meniscus, and that way we can use the initial and the final volume to find out how much total volume that we used. Okay, so when the burette's ready, now we have to prepare our solution, the one that's being analyzed. Okay, so at the end of the experiment, you guys told me the molarity of the HCl. Okay, so what we do is we put the solution, so I think we added 10 mils or so of the HCl, and then we added some water, about 50 mils of deionized water. Okay, we have it in a clean Erlenmeyer flask. Okay, if it's a solid, okay, you can have acids that are solids. You have to be sure it's completely dissolved. Okay, but ours was a solution, so you don't have to worry about that. Okay, then we put our stir in there and we placed it on top of the stir plate. Okay, and the last thing we had to do is add indicator. So I had a couple groups that forgot this, so guess what happened? It never changed color, right? Okay, so you have to be sure you add a few drops of the indicator. Okay, so then we just deliver our titrant to our solution that's being analyzed. Okay, and so we saw those flashes of pink. Okay, so as we got closer and closer, that pink kind of persists longer. Okay, but it disappears while stirring. Okay, and then as you get closer to the end point, okay, technically we're supposed to just take a wash bottle and kind of rinse the sides of the flask. That's to ensure that all the base is getting down into the flask. Okay, so that's not on the sides, okay, because technically whatever's come out of your burette should be in contact with the solution below. Okay. Okay. So if you're using a different indicator, you need to look up, what color should it turn or what should happen at a certain point. Okay, but for phenolphthaleins, the one that we used, I told you guys it would be a light pink for 15 to 30 seconds. Okay, if you think you have reached the end point, okay, you can record the volume. Okay, so I think I went around and told some of you to do that. That way, if you go past it and it turns fuchsia, so if it turns this color down here, you've at least recorded the volume previously. Okay, and that way if you go past, then no big deal, you already had your recording from earlier. Okay, and at this point you also, so you're drop-wise, so you first kind of start out a little bit faster, and then you start going drop-wise. And you can even kind of maneuver like half drops almost if you want to be, you know, that precise, but that all just takes some practice. Okay, so this kind of pink or a fuchsia color is when it's gone too far. And then the last thing that we have to do is we have to record to 2 decimal places the endpoint. Okay, so once we had the color change, now we record the final volume, then we subtract the 2 to give us the total volume. Okay, and then from this volume, we can do calculations. Okay, so that's what we're going to do next. We're going to do calculations. Okay, on most of the exams, so last exam we had some definitions, that kind of thing, but I haven't really had anything where you have to explain to me a certain process. Okay, I'm going to go ahead and tell you, because for some reason this gets everybody on the next exam, you're going to have to explain a titration. Okay, we've done this in lab. Okay, we have seen it on a video in there. There's also a video link if you want to look at the one up top, but didn't feel that necessary since you've all done it in the lab. Okay, now we've walked through and talked through each step. Okay, so when I mean explain, so I had a graded exam yesterday, and I explained, which was not, all people said was it changed or it's different. Okay, explain means to walk through each of these steps and tell me how would you do a titration. So if I was to pick up your paper and I'm going to read your experimental procedure, I should be able to pick it up, go into the lab, and do exactly what you have written down and perform a titration correctly. Okay, so that will be one part. I think, I don't remember what it's worth, at least 10, 15 points on the next exam. So be working on that. Correct grammar, that kind of thing. Yes. Okay. Yes. Yeah. You don't have to like make up numbers or anything, but you would just say, okay, I need to record the initial volume to 2 decimal places. Then at the end, you want to say, okay, I got to record the final volume. Either way, it's fine. You can do it stepwise. You see procedures that way, or you can do it in one long paragraph. Yeah. Okay, any questions on this? Okay. Next, we're going to look at calculations with titration. So on the exam, I'm giving you hints. You talk about a titration, you give me the steps, and then we do calculations with the titration. Okay, so while we're doing these word problems, I want you to kind of think about how you would do this in the lab. So it'd be the same idea, but in a word problem, I actually am going to tell you, okay, your final volume, or you use 31.7 milliliters of base. So you have to be given that data that you would have gotten experimentally when you were in the lab. Okay, these calculations, so if you got the ones from last exam, these are very similar. So we won't spend too much time on these, but we want to go through these. Okay, so we have HCl, so we have the exact reaction that we performed in the lab. So our neutralization reaction of HCl and NaOH to form salt plus water. Okay. So we know in the titration that we have 36.7 milliliters of hydrochloric acid. Okay, so that's our HCl. So that would be in our Erlenmeyer flask below the burette. Okay, and you guys measured out exactly, you knew exactly the volume of the acid. Okay, you didn't know the molarity, but you knew the volume. Okay, so you know the volume of the acid. Okay, and then once you perform the titration, you find that you use 43.2 milliliters. Okay, so that number was experimentally found in the lab, right? Okay, you found that you used 43.2, hypothetically. Okay, you also know your standard solution is 0.236 molar sodium hydroxide. Okay, so you have to know one concentration to be able to do this. You have to have a standard. Okay, and now we want to find the molarity of the HCl solution. Okay, when is this useful? Why is this useful? Okay, many times we will get acid solutions or different, whether it's basic or acid solutions, that we are not sure of the molarity, especially if they've been sitting out for a long time, if they've, some of it's evaporated off. Okay, so we will take that, whatever jar, whatever it's in, a flask, and we will take out whatever milliliters that we choose, or we may take all of it if it's a small amount. We place it in the flask, we titrate it with our known standard of our base, and we find out the molarity of the acid based upon that. So we don't have to make up a new solution, we can find the molarity that way. Okay, so we're looking for the molarity of the HCl. Okay, so if we look at this problem, where do you think we're going to start? Okay, we're looking for molarity of HCl. Okay, so whatever you're trying to find is going to be used later. Okay, so we want to look for also what we know the most about. So we know the molarity and we know the volume of the NaOH. Okay, so that's where we're going to start. Okay. Okay, so just like in our previous unit, if we take the volume, maybe moving to the board, hang on. Take way too long. Okay. I can try to write it like this, but it's going to take a long time. Okay, so we take our volume. Okay, so if we have milliliters and we have the molarity, if we take volume times molarity, what does that equal? If we rearrange our molarity equation. Moles or millimoles, right? Okay, so here we're in milliliters, so we're just going to stay in milliliters. Okay, and so if we multiply times molarity, okay, molarity is equal to millimoles per milliliter, or moles per liter. Okay. Okay. There's our millimoles. Okay, and this is all NaOH. You can put that. So if we take volume, if we rearrange our equation, molarity equals moles over liters or millimoles over milliliters. Molarity times the milliliters will give us millimoles. Okay? So now we have the millimoles of base. Okay, and so, but we're looking for molarity of the acid. So we know we have to use our balanced equation because we're going from units of NaOH to units of HCl. Okay, so we have a 1-to-1. So we have 1 millimole. There's our base. Okay, so we're going to stop here. We're going to get our millimoles. So just the 2 steps. Okay, so basically all we're doing is multiplying 43.2 times 0.236. Okay, so we end up with 10.2 millimoles HCl. Okay. Okay, we're looking for the molarity. Okay. Molarity is equal to millimoles over milliliters. Okay, so we just found, we're looking for the molarity of the acid. So we just found the millimoles of our acid. Okay. Now all we have to do is plug in the volume. Okay. Okay. So if we look back at our equation, what was the volume of the HCl? Okay, so we get 0.278 molarity HCl. Okay, so we have our standard base. We have the volume that we used, that we found experimentally, or would have to find experimentally. We have the molarity of our base, and then the volume of our acid. So we go from milliliters to millimoles of acid, and then we just plug it into the molarity equation. So you go back and find your milliliters, plug it in, and so we would have an HCl solution that's 0.278 molarity. Okay, in the second one, we have an acid that is a solid. Okay, so we have 0.3641 grams of KHP. Okay, KHP is just abbreviated for potassium hydrogen phthalate. Okay, so it's just an acid, and I go ahead and I give you the formula weight. Okay, so you don't have to add it up, but it's C8H5KO4. Okay, so we know whenever we're given grams, that would be a good place to start. Okay, so this time we have the grams of our acid, and we have 20 milliliters of NaOH, but we're looking for the molarity of the NaOH. Okay, so this time we know the mass of our acid, and we're looking for the molarity of the base. Okay, so we're going to take our grams and convert to moles. That is. It's probably about to all go away, sorry. So convert from grams to moles. Okay, this is all KHP. Okay, we have a 1-to-1 ratio again. I think the next two problems we have, well, I think it's the last one we don't have a 1-to-1. Okay, but it is common to just have a 1-to-1. So we have 1. Okay, so this is our KHP. NaOH. Okay, so we stop here and we find moles of NaOH. So it should be 0.00173, I believe. Okay. Moles. Okay, molarity is equal to moles over liters. So we go back and we see that we have 20 milliliters of NaOH. Okay, so we convert that to liters. We get 0.0200 liters. So the molarity of the base is 0.08915 molarity. Okay, any questions on number 2? Bless you. Okay, has everybody got this? Because I'm going to scroll down. I'm going to get another solution for drawing. Second. Okay, I want you to work 3 and 4 if you don't already have these. Write down 3 real fast if you don't have it, because I'm about to have to pull this down for a second to get my iPad in sync with the computer. Everybody got that written down? 41.4 mils sodium hydroxide, 37.5 nitric acid, okay, if you don't got it, look, if you don't have it, look at somebody else's. It's about to come down for a second. Okay, so if we start with what we know the most about, here we have the volume and the molarity of our acid. We're trying to find the molarity of the base. Okay, so we would take our really purple there. Internet is so slow, I can't. Okay, so we have 37.5 milliliters. Zero 0.342 millimoles. That's not picking me up. Okay, so we take volume times the millimoles, then we have a 1-to-1 ratio again. We have 1 millimole okay. So we end up with 1.2 2825. Okay, so we find the millimoles of NaOH. Okay, any questions for this first part? Okay, so what's our last step going to be? Okay, so we're going to divide by the 41.4 milliliters, which gives us 0.0310 molarity NaOH. Is that what everybody else got before I did it? Okay, so number 4, go ahead and work it. I'll get my little paint job off of it real quick. Okay, so this time you have a 2-to-1 to 2 to 1 to 1 ratio. So you end up with a 2-to-1 for your acid and your base. Got to add up your molecular weights or formula weights. So we're looking for molarity of HCl. so where are we going to start? We're going to start with 39.1 milliliters or at 0.483 grams. Okay, very good. We have sodium carbonate. Did anybody add up the molecular weight yet? The formula weight? Okay, so it's about 106.0. Okay, it's always out of 1 mole. Okay, so we have our moles of sodium carbonate. Okay, so what's going to be our next step? Okay, so we have to get our mole to mole ratio, right? Okay, that's the only way we have a relationship between the acid and the base. Okay, so we have 1 mole of sodium carbonate in the balanced equation. So it's going to go in the denominator. And like Emily said, we have 2 moles of the acid. Okay, so we get that from our balanced equation there. Okay, so we divide 0.483 by 106, then multiply times 2. Okay, so how many moles of HCl do we have? Everybody agree with Emily? Okay. Okay, so to get molarity, we now divide by our volume. So we're in moles this time, so we'll need to convert to liters. Final answer is what? What's the molarity of the acid? Okay, yep. So we get 0.233. Okay, take one and pass it if you don't already have one. Okay, has everybody got this? It's about to disappear. Okay. Okay, this is what I'm passing around. It's the end of chapter 11. Okay. We're going to be balancing equations. Okay, but this time they're called redox equations. Okay, so we're going to be mass balancing just like you guys have done before. So if you had 2 hydrogens on the reactant side, you had to have 2 on the product side. Okay, so we're going to have to mass balance, but you also have to charge balance. Okay, so these are going to have charges in them. So we're going to balance with electrons. Okay, so hopefully these are going around. This is kind of your notes for this section. Also, the bottom here gives you all the steps so you can keep referring back to this when you're trying to work problems. Like I said, this is just the beginning of this. We're going to do more of this on Monday, okay? But it has to be given to you at some point. You've got to start learning these steps, okay? So you may pick up on them today, but more than likely, okay, you're going to have to practice and practice. But what's funny about this is usually this is the best part of the exam because students actually, keep trying and keep practicing these, and it ends up being, students do very well on this portion of the exam. Okay, so oxidation reduction reactions. These are also known as redox reactions. Okay, they involve the gain and loss of electrons. Okay, so far we haven't had this involved. We haven't had charges be involved. We've just had neutral carbons, hydrogens, metals, whatever they might be. Okay, a lot of our household chemicals involve redox reactions. Okay, so 2 things I just wanted to point out here. But for ammonia, bleach, and vinegar, hopefully you guys know this already, but you do not want to mix these together. Okay, so if you are cleaning or whatever, ammonia and bleach do not need to be mixed together. Does anybody know why? Okay, yep, it makes a chloroamine is what ends up happening. So, okay, so if you take ammonia and bleach is basically this hypochlorite ion here. Okay, you end up forming this. Right, this is a poisonous gas. Can also, nowadays we use more, technical things, but this at one point was used as a chemical warfare agent. Okay, so if you're in your bathroom cleaning and you mix these 2 together and you're in a small space, at which most people are, and you mix the 2, it could be, it could be deadly. I mean, most people get out and get away from it before, but you have to be careful. Also, if you mix vinegar and bleach, same kind of idea, but you form chlorine gas. Okay, and so we all know that chlorine gas is potentially deadly as well. So those are redox reactions, though. So we're going to look at, yes. Yeah, I guess, or with bleach, the chlorine, or are you talking about just... Yeah, chlorine bleach, though, or chlorine gas? What are you mixing with? Chlorine... Okay, so that is bleach, yeah. So it's the same thing, yeah. Same idea. Okay, if you lose electrons, okay, so this is the way I remember. If you have loss of electrons, this is Leo. Lost electrons, oxidation, okay? If you gain electrons, it's reduction. So you'll see where this comes into play later, okay? So like I said, I'm giving you all the points first, and then we'll start practicing. Okay, gain electrons, so I think of Leo and Ger, how I remember it. Gain electrons, reduction, lose electrons, oxidation. Okay, so the difference here, this is just kind of a summary of what we're going to be doing. When we're balancing redox reactions, we have to actually break them apart into what we call half reactions. Okay, so we're going to take the reactant and the product that look alike, and we're going to put them together in an equation. And then we're going to take another reactant and the product that look very similar, and we're going to put it in another equation. So we're going to have half equations. Okay. All right. When we have 2 different conditions, so we can have acidic or basic conditions. We're going to learn acidic first. Okay. Basic conditions, we do the same thing, except for at the very end we have a couple extra steps. So we're not even going to get to that today. Okay. That will be on Monday. Okay, we have to mass and charge balance, so that's going to be the biggest difference. Okay, and one thing also to remember, if we're in basic conditions, a base usually contains hydroxide. Okay, so we're going to have hydroxide. Okay, that's a polyatomic ion. It has a -1 charge. Those are going to be the ions present in our final answer. Okay? If you have an acid, you want to think H+. That's the definition of an acid. It forms H+. Okay, don't forget this positive sign here. It forms H+ ions in acidic conditions. Okay, so acid, H+, hydroxide, base. Okay? Okay, the steps are on this so that you can follow along, go back to this, but we're going to go through the steps on the lecture here as well. Oops. Okay. First thing we're going to do is walk through all the steps. Okay, and the first rules that we're going to use are going to be for acidic conditions. Okay, so what I encourage you to do, the handout that I just sent around, is make your own notes on there. So not every little detail is on there, but if something clicks with you and you think you should add that there, that way, if you don't look at this between now and Monday, which I hope you all will, but in reality, so but if you go back on Monday and look at this, you'll have seen the notes that you've taken for little tricks or tidbits of information that I give you as we're going through this. Okay? All right, first thing you have to have is your unbalanced equation, which will be given to you. So it'll be already written out, but if you had to write it, you would write it first. Okay, then you break the reaction down. So you break it into two half reactions. One's going to be an oxidation, lose electrons, oxidation, and one's going to be a reduction, gain electrons, reduction. Okay. Then we're going to mass balance. Okay, right here, this first little part's really no different. You're going to mass balance just like you know how to do already. Okay, if you've got so many atoms on one side, you have on the other. Okay, so you do this by adjusting the coefficients. Okay. All right, the only problem you're going to run into, and you may not always, so each reaction's different, okay, is that you may have oxygens on one side, but you don't have oxygens at all on the other side. Okay, so you have to add oxygens. Okay, the way that we add oxygens is by balancing with water. Okay, so if we have 4 oxygens on the reactant side and we have 0 on the product side, then we're going to add 4 molecules of water. Okay, if we need to balance hydrogen, okay, same idea. If we have 4 hydrogens on the reactant side and we have 0 on the product side, we're going to add 4 H+. Okay, this right here, circle, it's a plus, it has a positive charge. Okay, one of the most missed things here is just to write a hydrogen. Okay, it's a proton, meaning it's acidic conditions. Okay. Okay, this is the part that's very different for you guys. You have to charge balance. Okay, you're going to charge balance, so you have 2 half reactions. Okay, we've mass balanced them. Now we have to charge balance them. Okay, and how you're going to do this is by adding electrons. Okay, are electrons negatively or positively charged? Negative. Okay, they're negatively charged. Okay, so if you want to write down this as a little tip, you're going to add electrons to the more positive side. Okay, you want to balance them. If you have a charge of 4 on the left side, I like the number 4 today apparently, then you have to have 4 on the product side. So your charge has to be the same on each side for both of your half reactions. Okay? Okay, this step often forgotten. Okay, in the first example, we don't even have to do this, but if you have both of your half reactions, and say you've added 4 electrons and you've added 2, okay, your electrons have to cancel each other. Okay, so they don't cancel if you have 4 and you have 2. So you have to multiply through the equation to make your electrons equal each other. Okay, so if you have 4 and you have 2 over here, you're going to have to multiply everything through by 2 on this side. Okay, your electrons have to cancel each other. Okay, once you do that, then you add them together. Okay, and you simplify by crossing out like terms. Okay, so we'll see this here in a few minutes. Okay, for basic conditions, like I said, we won't get to an example of this today, but the easiest way, your book does a little different. I've tried it 3 or 4 different ways. The easiest way and the way for you to get the most credit on your exam is to go ahead and do steps 1 through 7, exactly the same that you would do for acidic conditions, even if it's basic conditions. Okay, that way if you don't get these last 2 steps, you've at least done the first 7 right. Okay. Then what we have to do is we have to go back. Basically all we have to do is change out those H+ ions. They need to be hydroxide ions. Okay, so we'll get to that on Monday. Okay, and then you simplify just like we saw with the other conditions. Okay, I'm going to walk through each step here. Okay, this is our starting reaction. Okay, we have tin and we have bromine. Okay, so we're going to break it down into 2 half reactions. The easiest way that I think of is you find the reactant and the product that look alike. Okay, so if we look here, our tin 2+ and our tin 4+ look alike, right? Besides the charge. Okay, so that's our first half reaction right here. Okay, so the first thing we have to do is we have to mass balance. Okay, we have 1 and we have 1. So we don't have to do anything, right? Okay, if it was not the case, then we would adjust it with coefficients. Okay, the second part is we have to charge balance. Okay, so we've broke down into 2 half reactions. We'll look at the second one here in a minute. Okay, then we mass balance, which we didn't have to do anything here. This one's the easy one. Okay, and then we have to charge balance. Okay, so if we add up the total charge on this side, what would it be? 2+. Okay, one thing I'm going to go ahead and say. This charge is multiplied times how many ever moles you have here. Okay, we only have 1 here, so it is 2+. Okay, so we have a 2+ charge, and then here we have a 4+ charge. Okay, so earlier when I said add electrons to the more positive side, electrons are negative, so when you add them, basically you're subtracting 2. Okay, 4 minus 2 equals 2 equals 2. Okay, does everybody see that on both sides? Okay. This is an oxidation reaction. Okay, if you break these 2 down, and we're going to do the other half as well, and you get an oxidation reaction and a reduction reaction, that is correct. We're going to look at how we determine that here in a second. If you get 2 reduction reactions, something's wrong. Something has to be oxidized and something has to be reduced. Okay, so you have to have an oxidation and a reduction reaction. Okay, this is a oxidation reaction. Okay, earlier when I said lose electrons, oxidation. Okay, this tin ion lost electrons. It's on the product side. Okay, so it had to lose it to form the 4+ plus 2 electrons. So lose electrons on product side, oxidation. Okay. Okay, so what's our next half reaction going to look like? Okay, this was the one we just did up top, so don't get that confused. I'm just bringing that to the next slide. Okay, if we take Br2 and we have to, so technically we should have shouldn't be balanced yet, so if we pulled it straight from the equation, we would have Br2 okay, so that's our second half reaction. It has to be a reduction because the first one was oxidation. Okay, so the first thing we do is mass balance this. So we have 2 bromines on the reactant side, so we have to place a 2 coefficient here. Okay, so mass balance first. Okay, then we have to charge balance. Okay, if we look at this right here, okay, what's our total charge on the left side? I heard 2, I heard 1. Charge. It's neutral, right? There's no positive or negative charge. So bromine gas, it's neutral. It's not an ion. Okay, so it would be 0. Okay? If we look over here, what's our charge on the right side? Okay, remember, it's -1, but you have to multiply through the coefficient. That's why you mass balance first and then charge balance. Okay? So it's 2 negative, right? Okay, so we have a -2 and a 0. Okay, so which side's more positive? 0, right? Okay, so we have to balance it by adding 2 electrons. So we have -2 and we have -2. Okay, so you can almost think of this arrow here as an equal sign. Okay, okay, bromine has to gain. Okay, it gained it on the reactant side. Okay, so even gain electrons, reduction, reactant. Think of it that way. It's on the reactant side. Electrons on the reactant side. Has to gain these electrons in order to form the product. Okay, so we have a reduction and an oxidation reaction. Okay, now we add the 2 together. Okay, so that's what we started with up there. This is our oxidation half. This is our reduction half. And now we add the 2 together. Okay, this is where electrons have to equal each other. Okay, for this example, it's really the simplest of the examples that we have. Okay, one reason being because our electrons already cancel each other. Okay, we had 2 electrons in both of our half reactions, so we don't have to multiply through by anything. Okay, so then we simplify. We look for like terms. Our electrons have to cancel. Okay, you will not have electrons in your product answer, or you've done something wrong. You forgot to simplify. Okay, so if we cancel out this, okay, and then we look for any other like terms. Okay, in this case, we don't have any. So we don't have anything that's exactly alike on both sides of the equation that could be canceled. So then you just bring everything down. So here's your reactants. You bring them down. Here's your products. Normally when I kind of set these up, I like to put my half reactions and have the arrows match up so you don't accidentally move it over and put a product on the reactant or get them messed up. Okay, so the balanced reaction should be this. Okay, now you can go back and check it. You should have 110 atom, 2 bromine, 2 bromine. So it's mass balanced. We look at the charge, we have a 2 plus, and we have a 2 plus, 4 minus 2. So your end product should also be mass and charge balanced. Okay. Real quick, I'm going to leave you with this one, okay? That way you can work on it, hopefully. Okay, do the same thing. This one's a little bit more difficult. Okay, so we need to do this one real quick. That way you can work on some of your homework and know these little tips here. Okay, we break it into our 2 half reactions. So here we're starting with iron 2 plus and iron 3 plus. They look almost identical, right? So that's one of our half reactions. Okay, if we mass balance, it's a 1-to-1. We don't have to do anything there. Okay. If we charge balance, okay, we have a 3 plus charge and a 2 plus charge. So we have to add electrons to the more positive side. Okay, so we have to add 1 electron. 3 minus 1 equals 2. 2. 2 equals 2. Okay? All right, it's oxidation because we lost electrons to the product side. So LEO, L-E-O. Okay, so there's our oxidation. Okay, so what's our second half reaction going to look like? Okay. A very common mistake is to not write down the problem correctly. You forget to write the charge or you forget to write the correct number of atoms. Okay, so be sure that you write it down exactly like it's written. Okay, try to do this quickly and then you can ask me questions. Okay, so we've got to mass balance. There's our second half reaction. We have 2 chromium on the left, so we have to have 2 on the right. Okay, what's our problem now? Oxygen. So earlier I said if we do not have oxygens, what do we add to the product side? Water. So we have to add how many? Okay. All right, this is another little tip here. Okay. If you add water, what else are you adding? Hydrogen. So you're going to have to, it goes hand in hand. If you add water, you're going to have to add H plus to the other side. Okay, so how many H plus are we going to have to add to the other side? 14. We've got 7 times 2. We've got 14. So we're going to have to add 14 H plus. Okay, you also just added a lot of positive charge to the reactant side, right? So more than likely, it's going to end up being your more positive side. Okay, so we are mass balanced, but now we have to add up charge. Okay, so let's start with the product side. What's our total charge on the right side? Okay, coefficient times charge, that's a 3, 6. And then do we have charge on water? It's neutral, so it's 6 plus. I'm just going to write that under here. Okay. What about the left-hand side?
12 plus.
Okay, 14, right? Minus 2 is plus 12. Okay. All right. So we're going to have to add 6 electrons to the more positive side. Okay. Okay, if we look back at our other half reaction that we did, okay, we came up with, on the previous slide, Fe, sorry, trying to hurry here, 2 plus yields Fe3 plus. Okay, this is our step where the electrons have to equal each other. We only had 1 electron in the first half reaction, which was our oxidation. Okay, this one's our reduction. We gained electrons on the reactant side. Okay, so what are we going to have to multiply through in our first? Yep, we're going to have to multiply by 6. Okay, this number that we multiply through does not change the charge. It only changes the coefficient. Okay, so we end up with 6 Fe2 plus yields 6 Fe3 plus 6 electrons. Okay, you could have these all linear. I just ran out of room. Okay, those are all reactants there. Okay, we did this so electrons cancel. So that cancels. And then we would look, we'll see examples, we'll have some more common terms, but I don't see anything that's identical here and here, anything else that we can simplify. Okay, so then we just bring it all down. So our final answer is okay, it doesn't matter what order you put these in, okay, as long as you have them on the right side. So all those would be there. Okay, that's a plus sign, plus Fe3+. So all you do is bring down all your products, bring down all your reactants. Okay, we'll pick up with this on Monday, but if you have questions on it before you leave, let me know. And I will see some of you at Makeup Lab. Otherwise, you have lab on Monday, so don't forget. Yes. Yep. Okay, on your way out here, Yolanda, quickly, yep. Ryan, Dylan, Wesley Russell, okay, Mason, Ryan, Dylan, Wesley Russell, Miranda, Katie Moss, Tyler Sims, nobody's up here, Hunter, Andy, Jacob, okay, Joey, Stephanie, Andrew, Cody. Y'all come on up front. Hang on. There you go. Okay. Tyler. Andrew, Cody. Oh, I don't know where yours went. Hang on. Miranda Stewart. Andrew. Okay. Dylan's not here. Wesley Russell. Miranda. Katie Moss. No Katie? Okay. Tyler Sims. Joey. Brock. Leah. Eric. Jameson. Maybe easier if I come to y'all. How about that? Jameson. Kumar. Anderson. Ooh. Jacob Young. Emily. Jesse. Thompson, right? Okay. There you go. Josiah. Justin Anderson. Taylor Thompson, not here. Jake. He was here. Oh, Clayton. Justin Lee. China. Wesley. Go. David. Not here. Robert. Not here. Tyler Cook. Alicio. Not here. Taylor. That's here somewhere. Caitlin Davis. Job. Andrew Jordan. Jobs. Jennifer. Not here. Heath. There you go. Brittany. There you go. Leon. Scott. Alex. Tina. Justin Davis. Okay. Darius. Oh, not to give you two. Sal. Tevin. Tevin. You still here? No. Mariah. Hayden. Jesse Davis. I think that was yours, yep. Okay. All I've got is Taylor, David, Robert, Alicio, Jennifer, Justin Davis, and Tevin. Is that it? Okay. Yes, I just thought you were here, but didn't have it on there. Okay, let me stop my